Okay, welcome to Introduction to Photonics. Now, we have been talking about semiconductor light detectors, and yesterday we went through some of the basic physics of semiconductor light detectors. So, essentially we have a PN junction diode on which when we illuminate the junction diode with light, you see a corresponding generation of electron hole pairs as long as the light has energy greater than the band gap energy. And then we saw that because of issues with respect to the carrier transport inside that medium, if you do not have an electric field, you have carriers, they are under the influence of diffusion, wherein the velocity is much lower, whereas if you are under the influence of an electric field, you can actually push out these carriers much faster. So, the response time of your photodiode is much better, and that is the region where we would like to operate. That's called the drift transport. So, to enable that, we have been considering a PIN diode, and we looked at some of the characteristics of PIN photodiodes. We defined this responsivity as eta multiplied by lambda, which is expressed in microns, divided by 1.24. Where eta is called the quantum efficiency, but maybe that is a misnomer, because when we talk about quantum efficiency, we talk about purely quantum effect. Eta has these three components, 1 minus RF and then also 1 minus e power minus alpha w, which are based on the structure parameters. So, the real quantum quantity is this zeta, right, which is what does zeta correspond to? That defines the fraction of electron hole pairs generated for photons that are coming into the photodiode, right. That is the conversion that determines the conversion efficiency. So, anyway, we came up with this expression for R and the responsivity, and we looked at the physics of how the responsivity changes as a function of lambda, and then we went on to improving the responsivity by adding an extra layer in the PIN junction, and that extra layer was such that it was creating a large differential in the charge density, and correspondingly there is a large drop in the voltage across that junction. So, when you apply an external bias, most of that voltage drop happens in that junction, in that PN junction on the right side, and if the electric field is high enough, we are talking about electric field magnitudes in the order of 10 power 5 volt per centimeter, then you have impact ionization happening, which gives rise to avalanche multiplication of your carriers. Okay. And then we stopped at the point where we said the responsivity of an APD is m times the responsivity of a PIN, where m is determined by the electric field, or in practical terms it corresponds to the voltage that we apply to this structure. So, based on all of this, let us just take up a couple of examples and try to solve those. I am going to pick examples from here, question number 9 and 11. Okay. Question number 9, we are talking about a indium gallium arsenide based PIN photodetector. The absorption coefficient is given, that should be as a function of lambda, but let us just say that absorption coefficient corresponds to what you have near the band edge. if the intrinsic region is about 2 microns long and assuming anti-reflection coating at the surfaces, when you are assuming anti-reflection coating, that means RF, that factor that we defined yesterday, RF is equal to 0, and then zeta is given as 0.9. We are asked to find the quantum efficiency, the responsivity, and then the bandwidth. Quantum efficiency and responsivity we have been discussing yesterday. The bandwidth we did not talk about very much. I'll talk about a little more detail today. Okay, so let's look at this. Let's see how we can determine these quantities. So go with example 1. So we have indium gallium arsenide. Indium gallium arsenide actually has a band gap energy of about 0.8 electron volt, which corresponds to lambda c, that is a cutoff wavelength in the order of around 1.6 microns. Okay. So, we said gallium arsenide has 1.42 eV, right, whereas indium gallium arsenide has 0.8 eV, almost half the band gap energy. So, that is the beauty of working with semiconductors. You add elements, in this case indium, and you are able to change the band gap to such a large extent, and so you can change the emission or detection characteristics of this semiconductor material over a wide region, right. So, 1.42 eV, if you say for gallium arsenide, which we were using for LEDs, right, that would correspond to a wavelength something in the order of 850 nanometers. Okay, so gallium arsenide LEDs would emit at 850 nanometers, and then of course, if you use gallium arsenide itself as your detector, then you can say that is going to be sensitive to 850 nanometers and below, right. The cutoff, the band edge corresponds to about 850 nanometers, that is the cutoff wavelength. So, below that wavelength or energy greater than that energy, you will have responsivity. Okay. But we are talking about indium gallium arsenide here, because typically the reason why people are interested in indium gallium arsenide is most of your optical communication. What is the band at which optical communication happens? Wavelength band? 1550 nanometers, right, 1.55 microns. So, we needed detectors for optical communication. So, indium gallium arsenide was actually proposed as one of those detectors. I should also mention that germanium is another popular detector, not as popular as indium gallium arsenide these days, but before indium gallium arsenide was brought about, you had germanium as your detectors. Germanium has a similar band gap energy. So, germanium is sensitive to near infrared wavelengths. Okay. But let's look at this problem where we are given indium gallium arsenide, and we are told that we are asked to in the A part, we are asked to figure out the quantum efficiency. Eta which we derived yesterday as 1 minus RF zeta multiplied by 1 minus e power minus alpha times W, where W is the width of the intrinsic region, which approximately you can say is the width corresponds to the width of the PIN itself, because the P and N layers are the layer widths are much lower compared to the I layer width typically. Okay. So, in this problem we are told that this RF is 0, we have been asked to assume that RF is 0. This zeta is given as 0.9, and your alpha is given as 1 into 10 power minus 6 per meter, and your W width is given as 2.197 microns, so in 10 power minus 6 meters. Right. So, it is just a direct substitution once you recognize this. So, e power minus 2.17 multiplied by 0.9, if you do the math, it will come out to be about 0.8. Okay. So, does it have a unit? No, right, we are just talking about fractions and all that. So, that is eta is equal to 0.8. The second part is the responsivity. We have been asked to figure out the responsivity at two different wavelengths, 1550 and 1310. So, responsivity is given by eta multiplied by lambda, where lambda is expressed in terms of microns divided by 1.24. So, this is once again direct substitution. This implies that the responsivity at 1550 nanometers is corresponding to eta is 0.8 multiplied by 1.55 in microns, right. 1550 is 1.55 microns divided by 1.24, and if you do the math, I believe you would get 1 ampere per watt. Yes. So, question is whether this indium gallium arsenide is direct or indirect. It is actually direct band gap semiconductor. So, you can use indium gallium arsenide material for achieving lasers at 1550 also. They typically use indium gallium arsenide phosphide, where the phosphide actually finally determines the band gap energy.
So, for medium sources, we need always a direct semiconductor.
Direct, yeah.
Detection, we can use indirect also.
So, yeah, the question is, it is a good question. So, LEDs, we insist on having a direct band gap energy semiconductor. What about for detectors? So, for sources, yes, for the emission to happen, it has to be a direct band gap semiconductor, because you want to have this transition, the recombination happening without the need of generating this extra heat energy, right, because you want to maximize your conversion efficiency, radiative efficiency. But in the case of detector, you do not have that sort of constraint, because all you are trying to do is just take the electron out of the valence band, right. If you are just able to take the electron out of the valence band, you do not care whether part of the energy is going into vibrational energy and all that. So, you do not have as much of a constraint as far as detection is concerned compared to the emission. So, indirect band gap semiconductors can be used, but we have accounted that in the in zeta, that conversion efficiency. Indirect band gap semiconductors have lesser conversion efficiency compared to direct band gap semiconductors. Right. So, then we have been asked to figure out the responsivity at 1300 nanometers or 1.3 microns, and if you do that, you get a value of about 0.84 ampere per watt. So, a lot of times people wonder whether you can have responsivities of greater than 1 amp per watt, right? What do you think? Yes? No? Yes. Responsivity is just a numerical quantity. All the in terms of energy, the quantum effects are all absorbed in zeta, right? So, the responsivity can be anything. It can be even 2 amperes per watt. If you have a longer wavelength, you can get 2 amperes per watt. So, this is once again, people tend to think that responsivity should be a fractional value. No, it does not have to be less than 1. It can be greater than 1 also. But what you see here is it's roughly equal at 1550 and 1300. That just goes back to what we were discussing here. So, 1550 is probably here, 1300 is probably here. So, we are just riding this curve over here. Okay. Any questions about this? Then we will go to this other topic, which is the bandwidth of the PIN junction diode. It is not something that we talked about yesterday, but if we consider a PIN structure, PI and N structure, if you can tell that the response of the PIN structure is going to be limited by 2 different quantities, right? One is that you may actually generate some carriers in the P region itself or in the initial part of the I region, and as far as the electrons are concerned, in that case the electrons have to transverse across this entire structure. So, we are talking about an electron hole pair that is generated, an electron hole pair that is generated over here, and we know that the holes are going to move this way, the electrons are going to move this way, but the electron would have to transverse that entire structure before it generates this external photocurrent. So, in that sort of a scenario, you have a certain a finite amount of time for transiting across that structure. So, that is going to be the limitation as far as the bandwidth is concerned. It will not be like an instantaneous response, it will be a response that is delayed by the longest delay that you are going to see is corresponding to the case where the electron is going to have to transverse that entire structure, right. So, that transit time will be one limitation. The other limitation is like we talked about over here, when we have a pulse incident on this photodiode, you want this to immediately rise up, and when the pulse is going off, you want it to immediately come down, right. And there is actually one, we already said that the transit time is going to be a limitation in terms of generating the photocurrent, but the other limitation is also that the PIN diode is going to have a finite resistance, right, because these are not infinitely conducting. So, they have a certain resistance and they have a certain capacitance. Okay. So, what do we mean by the capacitance? It is basically saying that it is a structure that stores carriers, okay, stores charges, and there could be a certain delay involved in sweeping out those carriers, okay, which you can actually attribute to a certain capacitance of the junction. Okay. So, coming back here, when we are talking about the bandwidth, we will have to look at the response time of your PN junction diode, and that response time is going to have a transit time component and a component that is given by tau RC, which is the RC time constant. So, we know that the transit time will correspond to transiting across this entire structure. So, this is of width W. So, you can write this as W over the velocity, right, and the velocity typically that we are considering is the drift velocity, which depends on the external electric field. If the external electric field is 0, then VDR becomes that will be the diffusion velocity. So, so you are essentially if there is no external bias applied, then that velocity will be the diffusion velocity. Okay. And so you know that your diffusion velocity is typically in the order of 10 power 3 meters per second, whereas the drift velocity can be as high as 10 power 5 meters per second. Okay. So, there is 2 orders of magnitude difference. So, depending upon the external bias applied, the response of your photodiode can be 2 orders of magnitude different. Okay. So, the response actually can be made quicker with the external bias. You understand that, right? So, that is one important thing to realize. And the other case is tau RC, which depends on the series resistance of the junction multiplied by the capacitance. The series resistance works out to be in the order of a few ohms, and then the capacitance is given by epsilon A over D, right. In this case, if you look at the structure, the electrodes are over here. It's between this electrode and this electrode that we are considering. So, what is D here? That corresponds to the width of this entire structure, which you can approximate as W. So, you can write it as epsilon A over W. What is A here? Right, that corresponds to, if you were to put it in dotted lines, that corresponds to the cross sectional area over which the carriers are are going across, right. So, that corresponds to the area over here. So, there is actually a very nice engineering aspect over here. You can see that W happens in the numerator in the first term and W happens in the denominator in the second term. So, that is a contradiction, right. So, if you are trying to change W to change the response time, you are typically when you go for a smaller W, right, as far as your transit time is concerned, you have a larger capacitance associated with that. So, what do you do? How do you get around this log jam? The free parameter is A, right. A does not affect the transit time. Okay. So, if I want to keep this RC component very low, in the problem that you are given, you have been asked to assume that the RC time constant is negligible, right? How do you make RC time constant negligible? You can do that by keeping that capacitance very low. How do you keep the capacitance very low? By playing around with the cross section area. So, what you would find is, if you look at commercial photodiodes, you have these relatively run of the mill commonly available photodiodes, which are like large area, right, 3 millimeter, 5 millimeter active region will be there. And when you look at the response time for that, that will be in the order of microseconds or somewhere around that. Whereas you will have these specific photodiodes which are sold as high speed photodiodes. When you look at the active area of high speed photodiodes, you will find that they are tens of microns in diameter. Why? Because they are trying to play around with this RC time constant. So, for low speed photodiodes, you don't worry about the capacitance. It can be whatever, and so you try to keep the active area larger. But when you want to go to high speed photodiodes, it is imperative that you keep your active diameter small. If you keep the active diameter small, what does that mean from the responsivity perspective? It's harder to focus all that light onto that small diameter, so you may take a hit in the responsivity. Not all the photons are being absorbed by a photodiode, right? If you can't, let's say 50 microns is your active diameter, if you can't focus all your light to 50 microns, then you lose some photons, without even, they're not even entering that photodiode structure. Okay, so there may be a trade-off in the responsivity. You understand this? Light is falling from here, right? So, if this is the active area that we are talking about, that facet area, right? If that area is small, then you're going to have to focus all your light into that. Yeah, transit time depends on this W.
And response time depends on this. You said
Response time, well, so that's what we are saying. Response time in the case when you have negligible capacitance, as in the case that we have been asked to assume, you can basically neglect this, by reducing active area, right? By reducing the active area, you can neglect that part.
so area A.
Mm-hmm.
Which one are you considering?
Area A is the area of cross section across that junction. So that's actually the area of the facet, right? This facet from which light is entering. Okay, so response time is like that, and if the response time is like that, then if you plot the modulation transfer function h of f, what you will find is it's flat at low frequencies, and it drops down as you go to high frequencies, because it's limited by the response time. And what we are typically interested in is the 3 dB bandwidth. So, f3 dB is going to be given by 1 over 2 pi multiplied by this tau, right, which corresponds to the response time. In our case, we've been for this particular problem we've been asked to assume W as 2.17 micron and VDR corresponds to 10 power 5 meters per second. So, if you so that will, so this component, this transit time component, you will find is for this particular case that we are given, it's roughly about 22 picoseconds, and if you substitute that back in this expression, what you will find is this corresponds to 7.23 gigahertz. So, the bandwidth is 7.23 gigahertz for the particular example that we have given. Like I said, to get to that bandwidth, we are neglecting the RC time constant, which means that your area, if you go back and work out that area that you need to have so that the RC time constant is negligible, you will find that that area would correspond to something in the order of tens of micron square. Okay, understand this? Now, I do not have a lot of time, but let me just quickly work out this other example, or just give you a lead for that other example. Example 2, let us consider an avalanche design of an avalanche photodiode. Okay. So, I mean while we are at this topic, I should also mention that if you are talking about avalanche photodiode, you are just having one more layer added near the end region, but in terms of the response time, this response time will be there, because this corresponds to the transit time of these carriers across this entire region and the RC time constant. So, what you will have is this extra term over here, which corresponds to the multiplication. So, since impact ionization is sort of a serial process. So, you have one electron with a high velocity coming and hitting an atom and ionizing that atom, and then whatever is scattered from there can go and hit another atom and ionize another atom, so and so on. So, it is actually serially multiplying, right, and so that will have a certain multiplication time. So, this factor you need to add for APDs. Based on this, you can tell that APD response is going to be always slower compared to the PIN response, right? You understand that? So, because there is an additional multiplication time that happens in the APD. And if we go back and look at what we discussed yesterday, the APD without much bias actually has a M of 1. So, effectively at this point it behaves like a PIN. So, you take an APD and the bias voltage is 0, that effectively will act like a PIN photodiode. Okay. By controlling the external bias, you are actually controlling the multiplication factor, and that will incur a certain extra time, right, and that will limit the bandwidth of your APD. Let us just consider this region where the multiplication is happening, right. Let us say this is along x direction across that multiplication region. This is 0 over here, and this is W M, let's say, that's the width of the multiplication region. Okay. What is on the left side of that 0 location? That corresponds to the intrinsic region. What is on the right side of the WM region? That is the end region. Okay. So just give you a perspective of where we are. Now we can assume that we don't have any holes coming from this side, right? So because all your absorption has happened in the I region, so there's, let's say we don't have any more absorption happening beyond that, so there are no holes coming from this side. But there is actually a finite current. Let's call it the current density JE of 0 coming from here, and this is going to go through multiplication, and what we want to figure out is that multiplication factor. That multiplication factor that we want to figure out is JE of WM divided by JE of 0. Okay, we want to get an expression for that. And we know that as far as holes are concerned, they are actually 0 over here, right? So they go out as JH of 0 here, and here is JH of WM, which can be approximated as 0. Let's say that you don't have any holes coming from the end region, you don't have any absorption happening over there. Okay. So in this scenario, we want to find out the expression for M. To find that, we'll have to look at what is the rate at which things are changing across this junction. So let's say you have d JE over dx is what we want to find out. Okay. So what are contributing to this? There could be impact ionization due to electrons. Okay. So you have alpha E corresponding to the impact ionization coefficient for electrons multiplied by JE of x, right? So that is one contribution. Now the other contribution is you could have holes that are generated from the first impact ionization. They could also participate if they are sufficient velocity. They could also participate in generating other electron hole pairs. So you have alpha H and JH of x. Right? That's in a general case. Okay, you could have electrons generated due to impact ionization by holes. Now we need to solve this and get that expression for the multiplication factor. But solving that, we can have some assumptions. First of all, you have charge neutrality. Charge neutrality says that you are always generating electrons and holes as pairs. If you have generated an electron, there is a corresponding hole also there. Okay. So I can just say that dJE divided by differential of that current density corresponding to electron is going to be minus of dJH over dx, which is saying that electrons are moving one way, the holes are moving the opposite way, right? That is one condition. And you can also say that because they are always done in pairs, JE of x plus JH of x is a constant across this region, right? And let's just call that as a total current density. So the total current density is constant across the entire region. If that is the case, what is that value? That value would have to be this, because at Wm, Jh of Wm is 0. So that constant I can write as equal to Je of Wm, because Jh of Wm is 0, right? So those are the things, and of course we are assuming Jh of Wm is 0. So based on this, you can get an multiplication factor. I'll just put down the final value, final expression, and I'll let you actually do this yourself. The final expression that you will get is alpha e exponential of minus alpha e minus alpha h multiplied by Wm minus alpha h. Okay, so that is the final expression we get, and this expression, if you plot that, you will get something like this. M as a function of Vb, you will get something like this, which is showing an exponential. Let me stop at this point.